This chapter is about Riemann sums. It's a method of figuring out an area under a function to the axis. So, for example, if you have right here, here's a partial x squared function, and we want to know the area under this curve between 2 to 3. Now, what this is, so let's just go jump into it. So this is more of a geometry review. So example one, approximate the area under the curve y equal to x squared from x equal to 2 to x equal to 3 using four left endpoint rectangles. So what it means is, okay, here's my here's my function. I want to cut this into four equal rectangles. So and then each one has so that if I want to find I want to use rectangles to approximate the area. Now we know it's not perfect, so what happened? What left endpoint rectangle means is for the first rectangle, you have left side and the right side. But we're going to use the left side as the height of the rectangle. So it's going to cut across. So this first rectangle is right here. The second one, same thing. We're going to follow the left hand side and then cut across. You get your second rectangle, third, and then fourth. Now, we need to figure out the area for each one of these. Now, we know the width. Well, the width is 3 minus 2 divided by 4. Here we want to use 4 rectangles. So each one of these is 1/4. So therefore, we can figure out what are the x coordinate for each one of these places. So side 2, so 1/4 later will be 2 1/4, 2 1/2, 2 3/4, and 3. So now we have these markers here. And so each one of these rectangle has this length here, or the width. I guess the width is 1/4. Now how about the length? Now the length of the rectangle is the function itself evaluated at 2, because we want the left endpoint, 2 1/4, 2 1/2, and then 2 3/4. So if we plug in these, the first four value here start at 2, 2 1/4, 2 1/2, 2 3/4. You get the height of the rectangle. So here it is, right? So we're going to evaluate function at 2, 2 1/4, 2 1/2, 2 3/4. You get these. So these are the height of the rectangle. So to find the area, you simply take the width times the height of each one. First rectangle is 4. Second rectangle is 5.0625. Third rectangle, fourth rectangle together, you get approximately 5.71875. Okay. Now we're going to do the same thing again, but using the right endpoint rectangles. So this time, instead of using this side of the rectangle, we're going to use that side. Now you can see if we use the right hand side rectangle, so we're going to use the right side, move over, and then complete our first rectangle. The difference between these rectangles is this method, you're definitely going to be underestimate because you have these holes right here that you're missing out. And this will be the opposite. You actually be overestimate what the area under the curve is between 2 to 3. So we're going to do the same thing. The width is still 1/4, but this time we're going to use the right hand side. So we're going to use starting at 2.25 for the first rectangle. For the second rectangle, the height is going to be evaluated from 2.5, 2.75, and last one at 3. So we're going to do that. We're going to take those four values, plug into the original function. These are going to be these four numbers now. It's going to be the height of the rectangle. So to find the area, we take the 1/4, right, times the first rectangle, height times the second, height times the third, and then I'm sorry, height times the fourth. Then together we get 6.96875. Now both of these methods are not ideal, okay, because one underestimate, one overestimate. Now a better way of doing this probably using what we call the trapezoid rule. Now if you look, each one of these area under the curve is not really a rectangle. Trapezoid would be a better fit. Now the the area for a trapezoid will be what, base one plus base two times height divided by two. So if you look, we do have the height. Okay, it'll be the 1/4, right? That's the same thing. And we do have base one and base two, because base one is the left end. The left end, it was the left end of the rectangle, and then this is the right end of the rectangle. But now it's base one and base two for the trapezoid. So we do the same thing like what we did before, but we use the new formula. So the formula will be what, 1/2. The first rectangle will be base one plus base two times the the width or the height of the first trapezoid. Then we do the same thing with the second one. So it's 1/2. So to evaluate from 2.25 and 2.5, you get 5.0625 and 6.25. So these are base 1 and base 2, and times, again, the width, 0.25. And we do the same thing with the third trapezoid and the fourth trapezoid. Together, you get 6.34375. Now that, if you're just visually checking, is a pretty good approximation of the area under the curve, under this x squared curve between 2 to 3. Now, the actual area, now I know at this right now we have, in the next section we're going to teach you something called a definite integral. So what you're doing right now is, I know we're looking for areas, but if you evaluate, okay, if you take the integration of this y equal to x squared and evaluate that integration be from 2 to 3, you will get the area under the curve. So this is the physical meaning of integration, okay, or definite integral, which is coming up next section. So just jumping ahead a little bit, this is a preview of next section. We take the integral. We know how to take the integral of x squared, so it's x cubed over 3. Now we're going to evaluate from 2 to 3. So all you have to do is plug in the top number 3 into it. You get 27 over 3, and then minus plug in 2. Okay, so you get 19 over 3. So don't worry about this. We're going to go through this process in detail. But what I want you to see is the answer is 6.33333. So if you look at this answer and compare to the trapezoid method, it's really, really close. This is the actual number, and this is approximation using trapezoid method. Okay, now there's one more method that we can do is using what we call the midpoint. So since we know the left endpoint and the right endpoint is 1 over estimate, 1 under estimate, what if we find midpoint? So instead of using the left side or right side, we take the middle of the between the two, and then we go up, and this will be our first rectangle, second, third, and fourth. So what we need is what we need to find out the midpoint between the two. So that's the only thing that's a little tedious. So between 2 and the 2.25 is 2.125. Between 2 and a quarter to 2.5, you get 2.375. Between 2.5 and 2.75 is 2.625. And between 2.75 and 3 is 2.875. So these four are the numbers now you're going to use. You're going to plug into the function x squared to get the height of the rectangle. So the width is still the same, 0.25. These are the new heights. So if you take width times all the heights, right? Okay, this is another way to do the problem. Then you get 6.32. That's pretty close to the actual number, 6.33, and really close to trapezoid method as well. So the best method without using the definite integral to figure out the area under the curve is the trapezoid method or trapezoid rule, or using the midpoint for the rectangles. And sometimes the question they can give you in tabular form instead of draw out a picture. So that's simple. It's kind of nice in a way. This is better because they already evaluated for you. So the width, like for example, between 2 to 4 will be 2, and these right here, 10 and 13, will be the height, right? But depends if you want to use the left hand Riemann sum or right hand Riemann sum. You can always dot these points out. 210, the thing of its coordinate point. 210, 413, 615, 814. If you dot those out, you will see the picture and then see the rectangle underneath it. Okay. So if you want to do something like this to approximate a function between from 2 to 12, then all you have to do is if you want to use the right hand. Okay. So then from 2 to 12, then the first one is going to be from 2 to 4, so the width is 2. And then since we want the right hand, so between these two, the right hand side is 13, so we're going to use 13. The next one is from 4 to 6. From 4 to 6, again, the width is 2. And 13 and 15, which one we're going to use? We're going to use the right hand side. We do the same thing from 6 to 8. Their width is 2, and we're going to use 14 as a height. And last but not least, from 10 to 12 is still 2, and then we're going to use the I'm sorry, between these two, 8 to 10 is 2, and then we're going to use 9. And last but not least, 10 to 12 is 2, and with the right hand Riemann sum will be 3. So if you use that as 108. Now left hand Riemann will be exactly the same thing, except instead of using 13, starting at 13 all the way down, we're going to start at 10 to get it done. So if you start at, I'm sorry, if you start at 10, then it'll be same thing, 2 times 10, right? Because this is 2 in between, and 10 is the left hand side. And between 4 and 6 will be 2 and 13. 2 and 13, and so on and so forth. You use the left hand side, the left hand rearrangement, then you get 122.